Okay, good morning, everyone. Today we're going to continue our discussion of PCA. We're going to focus a little bit more on implementation today, but let's just review the main idea. So PCA is a way to take high-dimensional feature vectors. So we have vectors in RD, and we would like to approximate them using a linear combination of a few columns of this matrix B. So matrix B is going to have R columns, and so we have R approximation coefficients. So each one of these xi's is going to be represented by this zi vector, and ideally the dimension of those zi vectors much less than the original feature dimension D. And so to do this, we have to figure out how to design this matrix B and then how to compute the zi vectors from the xi vectors. So our objective for PCA is minimizing RSS. So this is looking at the sum of the Euclidean norms squared of the approximation error. And so we would like to minimize this cost function over the B and all our zi vectors. And this is exactly the task of PCA. And we'll talk a little bit about this more, but this is chosen, you could say, for simplicity. We can get a closed form solution. In general, we might want to do something a little different than this, depending on the application. But in that case, we're going to have a much more complicated method that won't have a closed form solution. Okay, so the solution that we saw to this problem is first you compute. Okay, first we are going to assume that the xi feature vectors, they're centered, meaning we've taken away the mean of them. And then we can compute the covariance matrix Q like this. And finally, we're going to do an eigen decomposition, and we're going to extract the R eigenvectors corresponding to the R largest eigenvalues, call those V1 through VR. We'll stack them in a matrix, call that capital VR, and that is one way that we can form this matrix B hat. You could also take VR and you could multiply this on the right by any orthogonal matrix, which essentially does sort of like a shuffling of these columns, then that would also work just fine for B hat. And what we're essentially doing is we are finding an R-dimensional hyperplane that best fits our data. So in the case that R is 2, we're finding a plane that best matches our data. And by match, we mean that the errors, these are the projection errors onto the plane, that the sum of the squared lengths of those vectors is minimized. So that's when we have a plane. If we have R equals 1, then our hyperplane becomes a line. And once again, we're looking to orient that line in such a way that the sum squared of all these projection errors is minimized. So last time we went through kind of a long derivation. When we first figured out the easy part was that to compute z hat, our z's, we just need to do this operation to the x's. And then the long part was figuring out how to optimize this dictionary. And in doing so, we talked quite a bit about the idea of orthogonal projection, where you have a vector and then you have a subspace, and you'd like to find the best approximation of that vector in the subspace. We said you can do this by multiplying that vector x by a projection matrix that we call PB that projects onto the subspace, which in our case is the column space of this B matrix. And this projection matrix looks like this. So this is something that shows up a lot in a lot of other contexts, so it's a very important concept. And then we also have the projection error, which is orthogonal to the subspace. And if you like to compute the projection error, you can multiply that, or you can multiply x by a different projection matrix, which is PB perp. So it's I minus PB. And these matrices have the important properties that they are symmetric and they are idempotent. So then we went through some linear algebra. We connected our cost, sum of squared errors, we connected that to the sample covariance matrix. And so then we did an eigendecomposition of the sample covariance matrix, and we found that because this is a positive semi-definite matrix, also symmetric, that the eigendecomposition has a very nice form where you have two orthogonal matrices, well, V and V transpose. V is an orthogonal matrix. Orthogonal matrix means all the rows are orthogonal to each other in unit norm. Same thing with the columns, they're all orthogonal unit norm. And then we have a diagonal matrix lambda containing the eigenvalues, and the eigenvalues in this problem are real and non-negative. We're going to assume that they're sorted from large to small, although depending on the solver, you may or may not get that when you actually compute the eigendecomposition. And then finally, the last step was proving that that if one minimizes our RSS cost, if you want to minimize this with respect to B, you can do this by choosing the R principal eigenvectors of Q. So we went through that proof last time. It was a little bit long, but so here's finally another summary. If you're given centered data xi, where I goes through 1 through n, you want to do PCA. What you do is you compute your covariance matrix, you compute the R principal eigenvectors of that covariance matrix, and you then stack those R eigenvectors into this matrix VR, and finally you can compute your z hats from xi this way, and you can compute your approximate xi's from the z hats this way. Okay, so that's essentially PCA. The kind of main idea is the derivation. So next we're going to talk about measuring the performance, implementing this, using this for classification and so on. Are there any questions before we move on? All right. So how do we quantify the performance of PCA for a given rank R? The reason we want to do this is at some point when we use PCA, we have to choose what R is. So we'd like to make sure that we have an R that's not too small and at the same time not too big. If R is too small, we're going to have a bad approximation. If R is too large, we're going to have a good approximation, but we will be redundant. We could make R smaller and have a more compact representation. Okay, so let's think about how we solved this problem in linear regression. When we wanted to quantify performance, we used R squared. And this is what we did in scalar linear regression. So in that case, we had 1 minus RSS over, you could say, the total target energy, n times the target variance. So for PCA, we're going to do something that is almost identical. We're going to call it proportion of variance, but when you look at it, it's essentially the same definition. So it's 1 minus RSS over, instead of total target energy, now it's the total feature energy. And in fact, if you did linear regression with multiple targets, what you would do is down here for s squared y, you'd replace that with trace of the covariance of y. And this quantity over here, we can also think about this as n times trace of the covariance of x. So essentially, it's the same definition. Okay, so it's familiar to us. All right, so let's figure out how we can write this more compactly. So we take our total energy. We can use the fact that this can be written as xi transpose xi, and then we can take the trace of that because it's a scalar, and then because we can shuffle the quantities inside the trace, we can move xi to the front and get this, and now we can move the sum inside and we get n times the trace of the covariance matrix Q. We can do our eigendecomposition of Q, and then we can do one more trick where we move V transpose to the front, and then you'll have V transpose V, which they cancel because V is orthogonal. So finally, the V's disappear, and you just have trace of n times trace of lambda, and that's because the diagonal elements of lambda are these lambda j's. That's just n times the sum of the eigenvalues. Okay, so this is looking at all of the eigenvalues all the way up to D, which is the full dimension. Now when you look at RSS, the top, so remember that RSS is n times trace of Q PB perp. Oh, sorry. We're usually writing it the other way, although it's equal in both cases. Okay, so it's PB perp Q like this. And so remember that PB perp is 1 minus PB, so if I minus PB. So if I substitute that in and use the linearity of the trace, we get this. And we just saw that this quantity above equals this, so we can write that here. And then we just have to deal with this quantity. So we also saw that the optimal solution for this trace PBQ, let's see, we go back over here. Remember, we were working on that. We were trying to minimize that. And we found that we could essentially, actually it's this one. We could write this guy, or maybe just the trace part, as this. And then we solved for the alphas, and we found out that we want to choose alphas that are either 1 or 0. We chose alpha equals 1 for the first R alphas and then 0 for the rest. So essentially, that's the solution that PCA uses. So if you plug that in to here, you just get a sum from 1 to R of the lambda j's. And that is what we have over here. Okay, so we have the total sum from 1 through D minus the first R components, which gives us the last D minus R components. Okay, so this goes from 1 to D, this goes from R plus 1 to D. And so finally we can write this expression, this expression here. We can write this down here. We'll write the 1 as this, and we'll write this ratio here like this, using the above. And they have the same denominator, so we can just subtract the numerator terms, and you can see I'm taking all D minus the last D minus R, which gives me the first R. Okay, so finally at the end of the day, proportion of variance as a function of R looks like this. So you can see that when you start out with a small r, this quantity is going to be small, but ideally, just like with r squared, we'd like it to be as close to 1 as possible. This guy will definitely equal 1 when r goes all the way to d. Our hope is that it gets close to 1 even when r is much less than d. And we'll see an example with our face data set that shows that, at least for that data set, it is the case. You can use r that's a small fraction of d and get this ratio to be very close to 1. Okay, so if we can make a plot of this versus r, we'll use that to choose r. Yes.
These eigenvalues are always less than 1?
The eigenvalues are,
That's idempotent.
let's see. I don't think the eigenvalues, no, the eigenvalues are not really bounded from above because they're just the eigenvalues of our data matrix Q, and they can be as large as we want. They're never negative because Q is positive, semi-definite, but they can be as large as you want. If you double R, your eigenvalues will increase. Sorry, if you double X, your eigenvalues will increase by a factor of 4. Okay. All right, so this kind of like finishes up the ideas behind PCA. Next, we'll talk about some ways to compute PCA efficiently, and this gives us an excuse to talk about the singular value decomposition, which is a super important decomposition from linear algebra. I think it might be one of the most important ones, if not the most important one of all the decompositions, in part because you can apply this to any matrix. A lot of the decompositions, like let's say eigenvalue decomposition, you can't apply an eigenvalue decomposition to a non-square matrix. So there's a lot of the decompositions that just are very restricted. But the SVD, you can apply it to any matrix. And essentially what the SVD tells you is that you can think of any matrix. If you think about this matrix as an operation, something that you apply to a vector through multiplication, then it says that that operation can be decomposed into 3 operations. The first one is a rotation. The second one is a scaling of each coordinate. And the third one is another rotation. That's what the SVD says. Okay, so these U and V matrices, these are orthogonal matrices. So again, these are matrices where all the rows are orthogonal to each other, all the columns are orthogonal to each other, all the rows are unit norm, all the columns are unit norm. But essentially, these are matrices that if you think about how they act on vectors, they can never change the length of a vector. If you multiply a vector by an orthogonal matrix, it always remains the same in length. But what can happen to the vector is it can be rotated around in the space. So that's why we can think about these as rotation matrices. Okay, so both of these guys here are orthogonal matrices, which we can think about as rotations. And then the S, this is a diagonal, which we can think about as scaling, coordinate-wise scaling. Now there's actually 2 forms of the SVD. They're the same conceptually, but they differ in the details. We have what I'll call the standard SVD and the economy SVD. Okay, so in the standard SVD, X and S are the same size. And U and V are square. Okay, and that makes sense. If I have an orthogonal matrix, it has to be square. Okay, so just as an illustration, maybe you have like, if X is tall, then you would have U would be a square matrix that matches the first dimension of X. S is a diagonal matrix that matches the dimension of X, and then V transpose has to match the right dimension or the second dimension of X. Okay, so this is what we have in the case of a tall matrix. In the case of a wide matrix, it would look like this. And of course, in the case of a square matrix, they would all be square. Okay, so that's the standard SVD. Standard SVD is a little bit wasteful in the sense that if you look at, for example, this. So this is all zeros. All this stuff off the diagonal in S is zeros. So for example, all of these are zeros, and all those zeros are going to multiply all of these. So these will be zeroed by this. So the point is, why are we even computing all these things here if they play absolutely no role in constructing X? So that's the idea behind the economy SVD. And in fact, even in this SVD here, we could have a situation where some of the elements on the diagonal are also zeros. So one of the rules about the SVD, I didn't finish talking about S. So S is formed by these diagonal entries SI. These are called the singular values. And the singular values are non-negative, but they can be zero. So you can have a subset of these guys also be zero. And so that means that all these guys here are going to be multiplying these, basically setting them to zero. And so there's sort of no point in computing these unless you really need, for some reason, that full orthogonal matrix. So the SVD saves computation by only computing the singular values that are non-zero, only computing the columns of U that will multiply those. And in fact, the same thing happens over here. If there are some zeros here, then those zeros will cancel out these columns of V or these rows of V transpose. So the economy SVD only computes the ones which are actually used in computing X. So in general, in the economy SVD, U is going to be square or tall, S is always going to be square, and V is going to be square or tall, or V transpose is going to be square or wide. So that's what we have for the economy SVD. So let's just look at the differences a little bit. So here, just to make sure the notation is a little different, I put the R there. So R is the rank. So the number of non-zero singular values of this matrix will be the rank. And as a result, this SR is a full rank matrix. It's a diagonal matrix with all non-zero elements in the diagonal. Okay, so let me try to say some of the important things. So this is square. And yeah, this is tall or square, and then this is going to be wide or square. So let me try to draw the situation, or a situation that could occur. You could have a situation like this. Okay, so this dimension has to match this dimension has to match this dimension, and this dimension has to be the rank of this matrix. So in this case, I drew a matrix which has a rank that's smaller than either of the dimensions. Okay, so the rank is at most the minimum of this dimension, this one, but it could actually be smaller in some cases. So this is important here. So in the regular one, you can have zero valued singular values, but in the economy one, they have to be positive. And that's what gives you this full rank. And when you look at these matrices here, this is a tall matrix with orthogonal columns. So that means that if I do U transpose U, that is identity. But it does not mean that U transpose is identity. U transpose, like in this case here, U transpose, you can see can never be the identity matrix. It's going to be a square matrix that's rank deficient. Right? Not identity. Okay, so this transformation is super useful because it allows you to sort of unpack matrix into components which are easy to deal with. The U and V are easy to deal with, they're orthogonal, and then the S tells you everything about the rank of the matrix, and you can prove a lot of different things using the SVD in linear algebra. Okay. How many of you guys have heard of the SVD before? Okay, great. So any other questions regarding the SVD here? All right. Okay, so we're gonna compute PCA first using the standard SVD, and then we'll show how to do it with the economy SVD. And in doing so, we're going to see the connection between the eigen decomposition and the SVD. Okay, so as before, we have our n feature vectors. We stack them into a matrix, as always, where the samples go down the rows and the features go across the columns. And we have data that's centered so that the sample mean of every column equals 0. Okay, so what we said before is that we can compute the covariance matrix just like this. 1 over n times x transpose x. And we also said we can do an eigenvalue decomposition, and because this is a positive semi-definite matrix, we know it's going to have V transpose, orthogonal matrices, and we know we're going to have diagonal lambdas that are non-negative. Okay, so let's say that I take this equation here and I plug in the standard SVD. So I plug in USV transpose for x. So that means that x is going to be USV transpose, and x transpose will be VS transpose U transpose. And the first thing we see is that we have this U transpose U quantity, which, because in the standard SVD this is an orthogonal matrix, that is guaranteed to give us identity. And so we can basically forget about it. And then we can, we have this, just for interpretation, we move the 1 over n into the center. And the point is that now you can see a direct correspondence between this eigen decomposition and this one here. So you can see that the V's that the eigenvectors returned by the eigen decomposition are the same as the singular vectors returned by the SVD. Furthermore, the eigenvalues are related to the singular values S in this way. So the largest eigenvalue, because here we're assuming they're sorted. By the way, in the SVD, they're always sorted from large to small, always. So we did that with the eigen decomposition just to make it easy to compare the two. Okay, so you see that essentially the ith eigenvalue will be the ith singular value squared divided by n. So there's a direct correspondence. Okay, so at the end of the day, lambda j is s squared j over n, and the V matrices are the same. Now there's sort of a little caveat to this. If the eigenvalues are distinct and sorted. It turns out that if you have a situation where you have two eigenvalues that are exactly the same, then there's no a unique way to get the two eigenvectors. You can do sort of a rotation in that two-dimensional space, and you get the same decomposition. However, with real-world data, I would say you will always have distinct eigenvalues. It's only with synthetic data that you could create a case where they're non-distinct. Okay, so that's basically the connection that even though originally we said PCA, you should use the eigenvalue decomposition, here we're saying, actually, if you take the singular value decomposition, you get rid of the u's, you use the v in the same way, and you just have to square and scale the singular values. You can essentially do PCA that way as well. Okay. Now, the thing about PCA is that we're not interested in all of the eigenvalues. We're interested in just the top R. And when we think about the Economy Svd, this is a technique which only computes the top little r. So in PCA, we're interested in the big R. R is the approximation. Economy Svd uses little r, where r is rank. Rank is less than or equal to the minimum of the dimensions d and n. In most data sets that you work with, you have many more samples than features, right? Usually, D is much less than N. There are a few exceptions. We saw a lab with an ECG or EKG lab where a patient wears like a helmet with like 30,000 little sensors, and then there's only 200 patients, and then you get basically a very, very wide X matrix. But in most cases, you have a very, very tall X matrix, lots of samples, not so many features. And in that case, you can see that when you compute the Economy Svd, you're focusing on matrices that are, you're going to take a shortcut, and like your U matrix will be at most n by d. It won't be a n by n matrix, which could be a gigantic matrix. Okay, so we're going to think now about the Economy Svd. Requires less computational complexity than the standard Svd. And for PCA, we need to compute only the top R singular vectors. And R is something that's even less than R little r. So this is kind of the ranking of all the different dimensions here. In fact, typically R is going to be much less than little r. Okay, so at the end of the day, we should be using the Economy Svd, not the full Svd, to compute PCA. So if we take our X matrix, we apply it to the Economy Svd, it will return for us this triple of UR, SR, VR transpose. And we know that VR contains more columns than we need. We actually need less. So we can just take the first capital R columns, this V little r, and that will give us the quantity we need for PCA. And then, that's our dictionary, and then this is how we can compute all our code vectors. Okay, so that's basically a really nice way to compute PCA just from this X matrix alone. You don't have to compute in terms of computation. If you say, well, why don't I just compute Q first and then take an eigen decomposition? Actually, there's a lot of computation wasted in just computing Q that you don't need to use And if you use the Economy Svd, you can actually compute these often in a faster way than you can get by computing Q first and then computing the eigendecomposition. So that's the idea. So don't need to compute Q for PCA. It's enough to compute SVD of X. All right. Everybody good so far on SVD stuff? All right. So now let's say that we would like to use PCA as a way of compressing our features before we do something else like classification and regression. So we're going to do an experiment with the face data set where we compress the faces to a smaller representation and then use those smaller features in order to do classification of who is the individual the face is, or the picture is showing. So let's imagine that we're going to do this. We're going to use them for classification and regression. And when we studied classification and regression, we decided that it was important to standardize our features. So now our features are actually the PCA coefficients z. Right? They're no longer the x's. We've left the x's behind. We've compressed them to z's. Z's are our new features. So when we do standardization, we want two things. We want that the mean is 0. So we'll call it z bar, which is just the sample mean. That should be 0. And second, the thing we want is we want that the variance of each feature j is 0. Right? So assuming that z is centered, I can compute the variance without subtracting the mean of z, because the mean of z is 0. And so if I want to know the variance of the jth entry, then I compute this. Variance of jth entry in z. And so I want that variance to be 1. I want 0 mean unit variance. That's the idea behind standardization. And I want this to be true for all my features j, going from 1 to capital R. Remember, R is our new number of features. Originally it was D, now it's R. So these are the two things we want. We can rewrite the second one in a way that might be a little more familiar to us. So first, in fact, we're going to leave the sum. We're just going to rewrite this part. So if we write this as zi transpose, let's think about that. So this is going to be a vector times its transpose. That's going to give us a matrix. Right? And here I'm saying I only want these squared entries. Those are essentially the entries that you will get on the diagonal of this matrix. So what you can do is you can just take the diagonal of this matrix, and that will give you all these individual, these are essentially the variances, because this is the covariance matrix. So on the diagonal you find the variances, the sample variances, and these are the sample variances you want to go to 1. Okay, so we're writing it this way just because, not necessarily this is something we want to implement, but just because we have been working with these covariance matrices, and we'll see that, that the derivation is straightforward if we write it in terms of the covariance matrix. Okay, so that's what we want. We want these things. So what do we actually have? So let's take our z bar here, and let's plug in our equation for zi. So we know we've created zi by taking our xi's and multiplying by VR transpose. Well, I can move VR outside the sum, and then I have the sample mean of the xi's, but remember that we have already centered them. So that is 0, so therefore z bar is also 0. So that's great. Basically, our z's are already centered. We don't have to do anything additional. Okay, what about the covariance matrix of our z's, this thing? So by definition, this is what we start with. Then we're going to do the same thing. We're going to plug this in for zi, and that's going to give us VR transpose xi, xi transpose VR. Of course, we can move the things out of the sum that don't depend on I, after which we have this quantity, which is, again, this is the covariance of x. So this is q. qx is different from qz. And let's do one more thing. Let's write q in terms of its economy Svd. So if you remember, we did that. Okay, so this is where we wrote it in terms of the regular Svd. Turns out with the economy Svd, you just have r's everywhere. Okay, so if you write this in terms of the economy Svd, you get this. Okay, and finally, let's think about these matrices, VR transpose VR, where the first you have the big R, second you have the little r. Okay, so V capital R is actually the first capital R rows of V little r. They're the same, because V capital R takes the first 4 rows, where V little r takes the first little r rows. I don't know if I said that right, but basically these are both just this is the first capital R columns of the V matrix, and this contains the first little r columns of the V matrix. So that means that when we do the multiplication, you get this. In the first capital R columns, because those are the same matrices and because they're orthonormal, you get identity. Now when you do the multiplication of this times all the columns of V little r that are beyond the first capital R columns, because all the V's are orthogonal, those give you 0. So essentially, these things simplify dramatically into these identity cascaded with zeros on either side, and this has the effect of simply extracting the first capital R elements in this diagonal matrix. So this diagonal matrix goes from 1 to little r, but now after you multiply it on both sides by this, it extracts the first capital R elements, and then so you have this SR squared, the 1 over n appears here. And so this is what we see for QZ. This is the covariance matrix. So it happens to be diagonal, which means that all the entries in our Z vector are uncorrelated with each other, but they're not scaled in the same way. The first one has variance SI squared over n. The last one has variance SR squared over n. If we want them all to have variance 1, there's an easy fix. All we have to do is multiply those ZI elements by square root of n to get rid of this, and then divide them by, Sj to get rid of this. Okay, so there's a very easy fix to standardize them. We'll call the standardized version Z tilde. So this is just the standardized Z. So again, if you compute the economy Svd, you have everything you need to do the standardization. All you need are those singular values, and it's very easy to do the scaling. Okay, we'll see this all in the Python code in just a few lines of code, but that's the idea behind standardization. Okay, and finally, let's get to the example. So we're coming back to our data set, which is labeled faces in the wild. And let's see what we do. So we first compute the mean of each of our features. That would be actually every pixel in the original images. And then we subtract the mean from those images to get this, call it XS. Then we can use NumPy's SVD command. This full matrices equal false is how we tell it to use the Economy Svd. And it returns for us U, S, actually S is a vector of the singular values, and V transpose. This is a little bit different than MATLAB. In MATLAB, you get USV, Python USV transpose. And just to verify that, we can look at the shape of V transpose. V is always tall, so V transpose should always be wide. And this is, in fact, a wide matrix, so yes, it's just as we expect. Now, in terms of this lambda, remember those are the eigenvalues. We know that those are just the squared singular values divided by the number of samples. So now we have our vector of lambdas. And finally, if we want to plot this proportion of variance or compute proportion of variance, this is just going to be a partial sum over the lambdas divided by the sum of all the lambdas. And this is a curve that starts out at 0 when you have 0 principal components, goes all the way to 1 when you have 1288 principal components, and in between it goes from 0 to 1. And as you can see, already at like 400 or so, it's almost exactly 1. So that says that there's a lot of redundancy in these faces. You can get rid of, you can keep, let's say a third of the coefficients, and that's an almost perfect representation. That 2/3 of it is completely redundant. Okay, so 400 principal components capture nearly all the variance of our data. Okay, so that kind of gives us a guideline. Now the other thing we can do is we can actually just do the approximation PCA and plot the results, because we're humans, we're used to looking at faces. We can look at the results that are generated and we can just get a qualitative assessment of how well this is working. So here you see for different R, so on R on the right, this is the full face without any compression. And then we have what happens if you use one singular value, one principal component, 3 principal components, 10, 30, 100, 300. And you can see that, yeah, at about 300, it's almost perfect. So we guessed 400 based on the POV plot, but it seems pretty accurate. And what's also interesting is just to see how the face evolves, how you start with a very canonical face, looks kind of like a mask. It's just from directly center. The light is directly centered. And then what you can see is as you increase more and more principal components to describe your data, it gets closer and closer to the full face. What you start seeing immediately is you start to see the shading change. The light is coming from the right and so on. And then even after, maybe even after like 30, you can start to tell perhaps who that face belongs to. Okay, so that's the approximations. Let's look at the principal components themselves. These things have been called eigenfaces. So first, remember that PCA requires mean subtraction. So we subtract the mean, and then when we build up the image, we're always adding on to the mean. So we should think about the mean separately. So this is just the mean image of all the faces in the data set. And that looks quite a bit like these. And then you have it ranked from the most important, second most important, and so are these are the principal components. The ones that are most responsible for energy in the approximation. And they're interesting when you look at them. They're mainly about, at least the big ones are mainly about the source of the light. Like this one is saying sort of the light source is coming maybe from below, a little bit to the right. This says the light source is coming from this direction. This says the light source is coming from there. And then you start to get, maybe certain features of different faces, and so on. But it's interesting to see, these are kind of the building blocks. These are the columns of that dictionary, the building blocks that you can put together to make faces in the most efficient way in terms of RSS. All right, any questions on these? All right, so now let's turn this into a classification problem. So we'll bring the labels back. And the code here is like a lot of the code you've seen all quarter. So first we do a test train split. We'll use a quarter of our samples for our test. We're going to center the training samples. So we compute the mean, subtract the mean. And we're going to compute the Economy Svd on the training data. We're going to choose R equals 100, number of principal components is 100. So then our eigenfaces, we're going to take this V transpose matrix, and we are going to just extract, we're going to extract the first NPC rows of it. In other words, the first NPC columns of V. And then it's very easy to compute the Z's. You just take your training X matrix and you multiply it times your eigenfaces transposed, your V transpose transpose, and you get your Z matrix. The last step is standardization. We have to take Z, we have to divide by the singular values, and then we have to multiply by the square root of the number of samples. So we were doing this. So now we have the data that's ready. It's centered, it's ready for classification. So we'll just plug it right into an SVM classifier. We'll do a search over the regularization parameter C, radial basis function kernel with gamma. Use grid search CV. And at the end of the day, it finds cross-validation accuracy with the best estimator is 85%, which is not bad. And again, this is for R equals 100. So, and then, that's the cross-validation estimated from the training data. We can, of course, apply it to the test data, and we get a 83%, which is pretty close. So, so it worked out pretty well. And this is with 100. So 100 is, these faces. Very last thing is to recognize some of the limitations. So it's a little bit dangerous when you apply PCA to the features in this way. In general, you should expect your classifier to get worse. So you're not doing this to improve performance. You're doing this to save computation, and in some cases for interpretability, but don't expect it to make things better. You're throwing away information, so it's probably going to be worse. Maybe not much worse, but... And here's a picture that illustrates why this can be, in some cases, disastrous for classification. So the main point is minimizing RSS is not well justified if classification is the end goal. So here's a toy data set, as you can see, where you have two classes. This is just a simple two-dimensional data set, classes 1 and 2. Let's say you applied PCA to this. Where's the line going to be? What's the subspace that best fits the data? It would be right here. Right? All those points would be that's the best subspace in terms of minimizing the approximation error. But as you can see, if I map all those points to a line, I lose the ability to discriminate between classes 1 and 2. If I want to discriminate, I should actually be doing the opposite. I should be projecting the classes onto a line here, and then all the class 1s are here, all the class 2s are here, and then I can have a nice linear classifier even in one dimension. That's what we have. Even in one dimension, we'll get perfect classification error rate. So this is just sort of a toy example to show you why PCA can do the wrong thing, because when it does its dimensionality reduction. It is not focusing on classification as the objective. It's focusing on approximation error in terms of RSS. Okay. So there is an approach that's a linear dimensionality reduction with classification in mind, and that's called linear discriminant analysis, LDA. It's a very famous old technique. I'm not going to talk about it any further. You can click on the link and learn more about it if you like. But that's the one. LDA applied to this problem would give you, a much better result for classification. It's not something that I see people using a lot today. It's sort of like a very old, simple method. So that's why we're not going to spend much more time on it. But I just wanted to let you know that this thing exists. It's a linear dimensionality reduction with classification in mind. All right. And one very last thing, just one more slide, or a couple more slides. A lot of times, the reason why we would like to do PCA is actually for visualization. Because we have a high dimensional data set, and it's really hard to understand what's going on. We would like to look at it somehow, but we can't look at it in high dimensions. So maybe we can squeeze it down to 2 dimensions and then look at it there. So here's just one example where I have a 3-dimensional data set with these different points here. These are in different classes. And it's a little bit hard to see what's going on, but if you use PCA and you approximate this, it will map everything, project everything onto that plane. And then when you look at the plane, you can see very clearly you have this data that is well clustered. And now if those are your different classes, you can say, oh yeah, okay, linear classification will actually work pretty well. Okay, so that's sort of the motivation. Let's say we want to do this with a more realistic data set like MNIST. MNIST is 384 dimensional originally. Here we're squeezing it down to 2 with PCA. The structure that you get is kind of interesting. You can see, so these are the different colors of the different classes. So the zeros are, I believe the zeros are this blue. The 1s are over here. The 2s are over here, and so on. So that's the representation. These are like the ZI hats for PCA on MNIST. And then this is a plot of the first principal component, V1. And red is going to be negative, I think. Yeah, red is negative and blue is positive. And you can see, so this is something that has kind of a peak in the middle and then it has a trough where the blue is. And you can see that what it's distinguishing, it's saying that if you're going to come up with just one vector to tell me what's most important about MNIST, it's whether there's like a stick in the middle or a circle around the outside. And it makes sense when you look at where the zeros are, they're over here, and the 1s are over here. So it's basically saying if I need to come up with a one-dimensional approximation of MNIST, it's going to be somewhere between zeros and 1s. Everything else is just somewhere in between. So this is the first principal component. The second principal component looks like this. It's a little bit more interesting. You start to see these building blocks for how you can make other digits, not just zeros and 1s, but other ones. And so, that's on this orthogonal axis now, how to make a 9. 9s are over here, or 2s, and so on. So it's very interesting to see how you can look at MNIST and decouple it and so on. However, PCA is not really doing a great job of splitting apart our classes, right? They're all crowded together. So then, what if are there better ways to do this? And the idea is yes. There are some nonlinear dimensionality reduction techniques, which are, at least one of them, tSNE, is explicitly designed for visualization. And so here's an example of PCA. This is essentially the same plot we saw on the previous page. Now if I use this method called tSNE, this is what it gives us. And now you can see it does a great job of splitting apart all the different digit classes. And the fact that tSNE can do this gives you some confidence that there exists a classifier that can also split things apart. Right, so this is something you can do maybe before you design a classifier to see, is it even possible to classify this data set? And if you can somehow do a dimensionality reduction that brings it down to 2 dimensions where it's separable, maybe non-linearly separable, but separable, then that's a good indication that yes, it should be possible to classify it. So that's tSNE, that's one of the most popular ones today, but there's some other ones. There's another one called UMAP, another one called PACMAP, but UMAP, you could say, works even a little bit better in terms of separating the classes. So these are things that are great exploratory analysis tools. If you're working with a new data set, you could try this stuff for the project to see what kind of pictures you get. You'll find that when you apply tSNE or UMAP, there are some parameters that you have to adjust to kind of make a nice picture, so it doesn't involve a little bit of tweaking, but it can be done. And there's a lot of other older dimensionality reduction techniques like kernel PCA, isomap, local linearly embedding, and so on. These are they've been around for a couple decades. They don't work nearly as well as these new ones like tSNE and UMAP, at least for data visualization. So that's all I had for this unit. And yeah, are there any questions on anything? All right, great. So then we're getting close to the end of the class. We just have one more unit left, and I think we only have 5 more lecture periods. I think I'll be able to cover that last unit in 3 lecture periods. That means we'll have 2 where we won't need to have class. You guys can just have those days off. All right, so we'll get started on the next unit, but then, and the next unit's on clustering. Someone told me they're interested in clustering, so we'll study that, and then we'll be done. All right.